specifically what I would like, okay, what I would like to do here, maybe before we get to it, is maybe in get you to think about different aspects of this. So, for instance, if you think about the concept of teaching field in second semester, how do you introduce a subject? What's your best way of getting into this? Do you use visualization, simulations? Do you think they help? You know, the usual thing, you got a force, field, potential, they all come right after the other. Is that confusing? Do the student get all of those things mixed up? And how about the textbooks? Are they good ones? Are they better ones? Are they helping? Do they hinder understanding? And also, since most of you are probably seasoned teachers, so you know what the challenges are. What do you think? What is the most common challenge? We know there's a lot of vector addition, a lot of math, especially if we're focusing on the calculus-based version of the course. What did you find that worked? Group work, examples, worked out problems, tutorials. What did you try that you find that didn't help very much? Do you have any other ideas about what could be said or done about this? So my thought here was just to kind of plan these things in your head and get you thinking about all of this. And if you want, at any point, I would be very happy to have you jump in to the discussion and, share with us what you think about any one of those or anything that I didn't mention here. Okay. All right, so then for the discussion for today, we selected two papers. The first one I'm going to focus, well, it's listed second, but I'll focus on this one. And it's an investigation about how to improve student understanding of electric field. And specifically, they're interested in how students perceive the problem of continuous charge distributions and how do they work out problems related to that particular topic. So this is a paper by Jingli and Chandralekha Singh from the University of Pittsburgh. And you can get to the paper through that QR code if you are interested. It's published in the PR Education Research, FISRA Education Research. And so what they've done, and I'm not going to go through the whole paper here, I'm just going to give you a very short summary and then look at some of the details. So as I said, they're focusing on the superposition principle. How do students handle that? What kind of difficulties are they experiencing with that idea in the context of computing the electric field of continuous charges? They have developed a series of pre-test and post-test questions that they're using to calibrate the effectiveness of their intervention. And they've also developed a tutorial to guide the students into this process that they're using as an intervention. So they go through the usual process. So they have multiple sections of the course. Some sections when we're exposed to standard lectures and work through problems without any special intervention. And then all of the sections were given the pretest. And then some sections were, in addition, given the tutorial. So they worked on the tutorial, and then later they took the post-test questions. And so they wanted to look at whether having some students go through the tutorial would actually improve their scores on the post-test as compared to the ones who didn't take the tutorial. So here's a very short list of some of the difficulties that they've been able to document. These are things that they've observed. They've also consulted instructors on the subject. So students have difficulties with moving from discrete to continuous charges. They claim, for instance, that the field does not have the same symmetry with respect to the charge distribution. They always think about the field as radially out, no matter what the charge distribution may look like. They have difficulties looking at the three-dimensional aspect of the problem, and also setting up the integral when they have to do these integration problems. That was also a challenge for most of the students. And so what the questions that they've used as a post-it look like, I don't know if this is large enough, but this is just to give you a sense of what kind of question they're interested in. So that's a short little set of questions, and they wanted to know how the student respond before instruction, and then they will also look at how they responded after instruction. Okay, and so this was just a view of the PROS test. Then the tutorial itself, which is available online. So if you want to use a QR code, you can go directly. It's from their Google Drive. You can access the tutorial. All I did here is take a screenshot of one of the on the first page. And as you can see, it's a sort of step-by-step tutorial on how to do things, how to set things up, and they progressively walk them through the whole process of doing the integration by going at it in a very methodical way. Okay, and so that's what their idea was. And then in terms of results, so here's it's called the control that they've used. So they've had students who didn't take the tutorial. So what their scores were before and after the class. Okay, so that's just using the textbook and standard lectures. And then here they show what happened with students who actually took the tutorial, and they can see a significant improvement on the scores on the post. Okay, and here they've also divided the students in terms of their performance for the ones who didn't take the tutorial, and you can also see that the very different results in terms of the post-test scores. You can compare here for the ones who did take the tutorial, fairly uniform in the above 80%, whereas for the ones who didn't take the tutorial, then the better students, the ones who had a pre-test range on the near the top, did relatively well on the post, but the other groups didn't do so well. Okay, so that was their conclusion for the paper, and so this was an example of how to try to intervene in a class where the students are having this kind of difficulty with the concept of electric field. Okay, anybody would like to react to this or have any thought about this? Have you done something similar to this in your own classes? Or does this ring a bell for anyone? Does it resonate with anyone as far as the difficulties and the challenges?
I would say they have trouble. One thing I've always struggled with this, I'm sure a lot of us do, because this is a very abstract topic. When I'm going through and doing like the continuous charge distributions, I pass out a handout where they, at least, they copy down their notes on how to do it, but but the sheet itself has all the basic shapes like a infinite line of charge, a sheet of charge, a disk, a ring, and all that, and have them copy down what does the field look like when we're done, and what is the relationship for the field with respect to your position in space look like when you're done. So hopefully by the time we get to Gauss's law, they have an idea, oh, when I see a line of charge, I see 1 over r. When I see a point charge, I see 1 over r squared. When I see a dipole, I see 1 over r cubed. And so hopefully they're starting to make that connection between the symmetry of the charge distribution and what kind of relationship you have with distance from that charge distribution. The other thing is, as you said, and as they point out in the paper, they can't seem to visualize what this field looks like. So there's actually a picture they have to fill in what the electric field looks like for these different charge distributions. So hopefully by drawing it in, they can sort of picture it. By the time they get to Gauss's law, they can hopefully make that connection between the symmetries and the charges. But it is, I mean, it's very abstract, and it's also very three-dimensional. So sometimes they'll draw out the 2D and they just still sort of lose sight that it is a three-dimensional shape, and they'll lose some of that information in there.
Yeah.
I think you pretty well nailed it there, Theodore. The 3D aspect of the fields is really troubling for students. In fact, anything that they run across in physics that's 3D is going to be a struggle.
Yeah, John, you want to go ahead?
Yeah, so I don't think these are going to be different than your students, but I would say that one of the things that really hinders a student in this section, especially when you get to things like Gauss's and Ampere's laws, is a not very great understanding of geometry. But there are some really very, very basic things that I find I have to get through with my students to get them to be able to draw fields. So I do a short discussion, I do an example, and then I put them in groups and they answer conceptual questions or problems in their groups, and I walk around and help them. But one of the things that I have them do is I give them it's still the discrete case, a couple of discrete charges and a point in space. And I ask them to draw the electric field due to each of the two charges at the point in space. First question, is the point positive or negative? Because they remember fields point away from positive charge and they point towards negative charge. So I got to know if it's positive or negative, be able to draw. So it's just a point in space. There's nothing there. So part of it is understanding the nature of the source charge producing the field. Then when they finally draw something, it never starts at the point. It starts at the charge. And I have to really work to get them to start at the point.
Yeah.
But yeah, no, symmetry is hard to get to them. The finite rod of charge, if I give that on an exam, I will see a not insignificant number of people use Gauss's law to solve that problem, which obviously it can't be used in, well, okay, it can be used, but not
Yeah.
with
That's
that
it.
symmetry.
That's interesting, John. My students always start their field drawings in the middle of space, like the charge is over here in the field, they start drawing it way over here.
Huh, that's interesting.
Like there's a gap there. Like, okay, but what happens here?
Right. Yeah. Yeah. One of the questions I ask very often is, okay, so if I have a field that looks like this, so draw some kind of field somewhere, and I ask, well, where does that come from? And what could possibly generate a field like this? So they always focus on, oh, it points this way, so it must be positive. And I say, how do you know it's positive or negative? I mean, it's just a vector in space. How do you know what that is? And I don't know, there seemed to be something that they, maybe it's the radially out, they think of it going away, there must be a positive charge. And it takes a while to get them to realize, oh, it could be also a negative charge on the other side doing the same thing. But they always want to go with a narrower range of options and limit themselves to that. And if you say, oh, there's all the other options, then, oh, well, that's too complicated.
Corinne,
Yeah.
this is Chris.
Yeah.
I just posted in the chat. I found an app that's available both on iPhones and Androids, I believe. It's an augmented reality that is supposed to help students look at fields in 3 dimensions.
Oh, okay. So, okay, I'm not, oh, I see. I haven't seen that yet. Okay, that would be interesting to check out. I'm sure. Does it require? So it's just on a phone or just on Android? Doesn't you don't need a 3D VR thing or I know that stuff, right?
No, but you do need a cube, but you can print off. Like they provide a link, and you basically print off. It's like a 3D QR code. Then you print it off, and then you tape together the cube, and that's what's used for the app to figure out what to focus on.
Yeah. Okay.
Oh, I attended a workshop with one of those, and it was very interesting. At the time that I did it, it was still in the very, very early stages. So this would have been like, oh gosh, 4 years ago, maybe. But the visualization that they had created with this little 3D cube was actually quite phenomenal. It was pretty cool.
All right. Did I see your hand, Maggie? Did I see your hand up?
Yeah, Maggie.
Yeah, so I was one of the things I was going to add about the difficulty I find in teaching this, especially when it comes to the continuous charge distributions and Gauss's law, is they don't know what an integrand means.
They don't know what? I'm sorry, I missed that.
They don't know what an integrand means.
Yeah, okay.
Like, what does DQ mean? they know the algorithms for calculus.
Mhm.
They can do the algorithms for calculus, but when it comes to actually applying what that thing means to a physical thing, I have to spend a lot of time talking about, okay, what is DQ? And talking about the nuts and bolts of the E equals integral K DQ over R squared, like R hat. So like what are the nuts and bolts of this equation? What does all of this stuff mean? And I asked them a question like, okay, guys, here's our equation. E is integral K dq over R squared, R hat. How many variables are there in this equation?
Mhm. And they
Some of them will say 2, some of them will say 3,
right.
because they might think that R hat is a variable. They don't understand the unit vector yet, although they are, it's the first week of class. They're mostly taking Calc 3, so they have seen unit vectors a little bit in Calc 3. A lot of them are taking statics, so they've seen unit vectors in statics. They're seeing unit vectors in my class. So they're a little familiar with it, but they're not there. But, getting the idea of, okay, we've got to relate DQ to R somehow. How do we do that? The density, charge density, and working from there and understanding. And then, the other bit of that is being able to relate, okay, what do the limits of integration mean for our problem? And do your limits of integration match what your integrand is? So if you're doing an arc of charge and you're integrating over d theta, are your limits of integration angles? So that's a thing that I have to work with them a lot. And it doesn't help that when you read textbook examples, textbooks all treat these problems like, here's the special trick, here's the special trick, here's the special trick. You're going to do this special trick for this shape. So memorize all these shapes. And like, guys, no, there's a method.
Yeah.
It's vector addition. Let's talk about how we apply vector addition to this. So yeah, and this is something close to my heart because this has been my last week and a half.
All right. Theo, I think you had a hand up. You want to jump in?
I think Maggie hit the nail on the head. It's just there's just so much in there. And I've downloaded some papers, I think by Reddish, where he talks about, and I haven't read them yet, so I apologize, but I think what he was getting at when I was looking at the abstract was that, as Maggie pointed out, there's so many things in this equation for them to parse apart and figure out what do each of these little pieces mean, and they're so new to it they can't seem to hold all these different things in mind simultaneously. One thing with the DQ is I always try to make that connection to geometry. We're trying to integrate the geometry, and so we need to write that DQ in terms of geometry. And one way I do that is in the first semester when we do moments of inertia, we do a very similar integral where we take the dm and relate it to geometry. And so I try and they never remember this second semester, even though they've done it first semester and they've done it in their calc class and they all hated it in their calc class, so they forget about it. They want to forget about it. But yeah, we just reinforce that over and over again is one way I have to try and get them to see, because again, the way we do it in physics, first year physics, we assume they haven't taken Calc 3. To me, this all made much more sense after I'd taken Calc 3 and taken a more advanced D&M class. And then those are all easy for me once I could see the Calc 3 way to do it. But we're kind of, as Maggie pointed out, they all seem like little tricks to them because we're trying to do this with the tools of Calc 1 and 2 and not vector calculus, so they can see it in all 3 dimensions easily. Thank you.
Yeah. Cyrus, I think you had your hand up. You wanted to jump in?
Yeah, I just want to plus one the comments that were made and throw in one specific example. One thing that I've found when I've taught Gauss's law specifically is students find it a little bit intimidating that if you have the integral form of Gauss's law, for example, you're dealing with vectors on one side of the equation, the E dot dA and the dot product, but then you're dealing with scalars on the other side of the equation, Q enclosed and epsilon naught. And there's this weirdness where if you understand the dot product and how it transforms vectors, then it makes perfect sense. But for whatever reason, seeing dot product and integral and scalars all together, all at once,
Yeah.
just it can be very intimidating.
Yep, you're right. Absolutely about that. Yeah, Anthony, you want to jump in?
Yeah, so sorry, let me lower my hand. I think we probably, we were talking a little bit like visualization before. And I'm guessing we all use like some sort of like tool to kind of, help students like visualize what's going on in the electric field, especially like with continuous charge distribution. I guess last fall, I came across a simulation that maybe you're already aware of. It was new to me, so I'll just kind of share. Like, I don't know if I think it's helped a little bit. I haven't like done any studies about the impact, but can I maybe share my screen real quick, or
Sure, yeah.
is that okay? Okay,
Let me
me
see
I can-
how I do this again. I need to
Yeah.
go to.
I might just be able to take over.
Yeah, you should. Let me see.
I think I took over.
Make.
You're seeing Fat?
No. Oh, you are. Yeah, you're.
Looks
yeah,
like you're a
you can
co-host,
take over,
Anthony.
Yeah.
Yeah. Okay.
Okay.
Yeah. So
you-
so this is. I mean, you're probably all familiar with Fat in terms of like
Let me
like
stop
building
sharing
the
then.
line of charge, right? Or are you seeing my screen, or sorry?
Oh, yeah.
I think
okay.
you are. Yeah. Yeah. So I mean, I think like this is pretty standard, right? Like building, having the students build like a line of charge using FET simulations. And I guess one thing I've done, I started to do more of is like I would be up in the screen, like up in the, up in the instructor station, kind of driving. And I think I've decided to just let the students play around a little bit more and have it a bit more open-ended so that, they can play around with the simulations. But so this is not new, right? Like you're all probably familiar with this FET simulation. I guess the one thing I did discover last fall was like this series of simulations, like on, as a GeoGebra. I think it's by someone. I guess I probably should have done that.
Mhm.
I think it's like Dave Nero. I think he's at Pitt, maybe. And so yeah, he's put a bunch of all these simulations. If you haven't seen this before, I hadn't seen it until last fall, but he had this one about like integrating like for a line of charge, what I thought was pretty cool. Now you might have seen it show up really quickly before it kind of refreshed. Like for like while this is loading, you see some equations show up here, but it's going to disappear when that thing stops loading. But yeah, like you could kind of pick a point on this line and, or I guess let me try reloading again, because it's not just a static image. It should actually be some kind of animation. This is probably what let me maybe turn off my video. Maybe that's causing it to get caught up. But yeah, anyways, if the simulation were working properly, I would be able to like drag this little red triangle or little red rectangle and watch the vectors kind of like animate over time, so you can kind of see the components of the electric field. And then so like where this red rectangle is kind of corresponds to where the shaded areas are, right? So for calculating that specific component of the electric field. And as it kind of shows, right, like here's the area, like, so this is computing, right, the X component, the Y components. So you kind of get a sense as you kind of, integrate over the length of the rod, right, you see where that is like in the graph. And again, if this were working properly, I could, drag this around, see how the, integration changes. I could take this point where we're calculating the field and drag it around. I guess I'll try reloading one more time just to see if that actually does anything, but I guess it's
Yeah.
not. And then you'd see the graph change, and then I could take this little slider and change the charge density, and then you'd see the graph change as well. So
Mhm.
I don't know if someone has seen this before, but I could share a link for anyone who hasn't seen this before.
Yeah, it's my first time seeing this. I think it's really interesting. Yeah, I'll play with it as soon as I get your link.
Sure.
Okay. All right. Let's see. Negusi, you had your hand. You want to add something?
Oh, I think most of the things have been said. I agree with all, but our problem, I think, is what I'm seeing is the students do not really relate the integration they learned to the physics, to the application. They just were given integrals and then they do integration, or the calculator does it. I think they just lack the concept of what does it mean to slice, what do you and then go from slice to slice. So that idea of application of the integration methods that they have learned, passing it and then using it here. So I tell them, I'm not going to teach you calculus. I'm just going to teach you how to use it to solve physics problems. So, and one of the problems when I was just asking question, what is that you are having difficulty with? And most of them say just setting it up. We don't know where to start. I think that was about, 18 out of 20 students say we don't know how to start. 17, sometimes 15, but they didn't know. So I had to come up saying, okay, whenever you see a problem, say, okay, find the electric field at this point. Then first of all, start with the, what kind of charge distribution you have, decide, and then slice and see the component, the vector form. But still, I made a little progress, but not as much as what I want to. So it is really a challenge, but I think it stems also their lack of really proper understanding of the calculus that they have learned. So maybe giving them like, okay, how do I start? The steps, there is a way to start it. And then I list 1, 2, 3, 4 steps to approach generic problems for those kinds. So that has helped a little bit, I think.
One of the things I've always wondered is, because I think there was an effort to think about that earlier, a few years ago, is about the grouping the physics and the math, the teaching concurrently, those topics. And there was even a textbook that had an integration of both physics and math. It never took off because I haven't seen it ever since I got that first edition. But do you think that's something, is it too impractical to have this merging of math and physics at some point, or some sort of different format to teach this particular subject? Because I have the impression that as long as they're learning calculus on one side and then we do the physics on the other side, that gap between the two is going to be, expecting them to bridge the gap themselves is probably a very challenging thing for them to do. Let me see. I think Maggie, I don't know, between Maggie and Cyrus. Maggie, go ahead.
Oh, I was gonna say you can let Cyrus go first. That's fine.
Okay, all right. Go ahead, Cyrus. Sorry.
Thank you. Just commenting on the integration of physics and math. I was lucky to go to a high school where the physics teachers and the math teachers were in constant communication with each other. And so one thing that I found worked really well, at least in my educational experience, was maybe not necessarily doing both the classes in the same, both topics in the same class per se, but having a lot of feedback between the departments or between the teachers and just kind of coordinating lessons. Now I fully realize that is very, very difficult to do in some settings, but it did work out very well in that particular case.
Yeah. Okay. Let me see. Maggie, you want to go ahead next?
Yeah, I was gonna say, actually, I was working, I initially thought about doing something like this within what we call on campus, our campus learning communities, which are linked classes where you have 2 classes together, students sign up for both of them, and then the instructors basically team teach the class. So I thought about doing something like this with Calc 3 and Physics 2. And I actually sat down with one of our math professors who regularly teaches Calc 3. And I said, okay, this is the calculus I need in week 1. This is the calculus I need in week 2. This is what I need in week 3. And basically what we ended up concluding was that, okay, you need surface integrals in week 2. If I'm lucky, I get to that in the last week of class.
Yeah.
So, and so we didn't really, after we looked at that, we didn't really pursue that very much. Also, I also figured out that it would be much nicer if I could do, if my students could take differential equations concurrently, because all the circuit stuff is just solving differential equations. So, yeah, I thought about this. I've also been considering that the standard calculus topical sequence is completely and utterly wrong. I've come to that conclusion over the last couple of years. Because they should, in Calc 2, they should start vectors in the middle of Calc 2, and they should take all that stuff with Taylor series and, you know, all the infinite series stuff that's in the back half of Calc 2, just pick that up, move it to the end of Calc 3 and shove everything forward. So yeah, I know that means you've got vector stuff now straddling those two classes, but if you want to serve the physics students, you know, because all of those students who are taking Calc 2, they're generally going to be engineering majors, at least in my experience. That, you know, so that them taking all that vector stuff starting in the middle of the second semester, reinforcing everything they've been doing in Physics 1 with vector addition, I think would serve those students much, much better. But I recognize that that is never going to happen.
Yeah, I guess so. Sherry, good.
Yeah, to address again this link question, one of my colleagues and I also were faced with this. It started over lunch when we were like, I know you're teaching this to the students. Why can't they do this in my physics class? And we started actually looking at how, and we also wanted to do a linked class, but that was totally shut down by the math dean. He didn't want to go with it. So we ended up basically doing a lot of visits of each other's classes. And one of the things that we found that was hindering the students is the notation. Sometimes physics uses different notation than the math classes use. You know, for example, for derivatives or for the chain rule. And, you know, I would start doing something like that in my class, you know, explaining some physics concept, and the students would look at me like I was talking a foreign language. And I'd say, what? You did the chain rule, right, in calculus? Yeah, but it didn't look like that.
Yeah.
You know, so she actually started showing alternate notations in her math class. At the same time, you know, she was doing what was in the textbook. And then she would come visit my class. I'd go visit her class. And in order to help reinforce that link, you know, between the two classes, because I think it was John who said it, the setting up. They can do the calculus, throw the calculus problem on the page for them. They can solve it, but can they build that problem?
Yeah.
That's where the problem lies. And so we spent a lot of time working on that. So yeah, I think a little more linkage would be a good thing.
Yeah. Well, speaking of notation, I always use as a prompt in my class just for fun or just for comical effect, the whole thing about the unit vector notation. I'm very traditional with my IJK. And I have a lot of students coming in with the bracket notation. And so I make a big fuss about it. I say, no, I don't want to see that. And one of the students even showed me, they were doing some group work, and he showed me the result with that notation. He did it right. But I said, no, I don't want to talk to you because you have this ugly thing there that I cannot approve of. And some of them, I mean, very few have this X hat and Y hat and Z hat. So I started mentioning at least the whole idea that, you know, notation can be very different, and we do things because, I don't know, we're comfortable with certain choices. We like them. There's no other reason, I think. I don't know. Why do we use IJK? I've never really learned about why that particular choice. Who imposed that on us? But anyway, so yeah, the notation is a big problem. Yeah. Okay, so. And yes, the linkage between the two would be a really fun thing to do. But yeah, as Maggie said, I don't think it will ever happen. Okay, so let me see. Let's move on then. The second paper, let me go back to my presentation. Actually, I'm not going to go back to it because for the second paper, it was actually about textbooks. So I'm going to go directly, and I didn't have time to do what I wanted to do here. So let me share this part. So this was the second paper that I listed in the, okay, why am I getting this here? Okay. Yeah, I need to make it a little bigger. So this study took a bunch of standard textbooks, introductory physics textbooks. So they're a group of faculty from Uruguay and Spain. There's 4 of them. And so what they did is they were interested in the way textbooks were presenting the whole theory of electric and magnetic fields. And they were looking specifically at the Maxwell's equations and how the textbooks explain the relationship between the electric field and the magnetic field within the context of Maxwell's equations, and also the electromagnetic waves. How do the electric and magnetic fields of the wave kind of connect with each other? And where do the fields come from, the sources of the field in all cases? And especially they were interested in the question of, how we use the variation of the electric field to generate a magnetic field, or the variation of the magnetic field to generate an electric field. And they thought it was kind of puzzling that the way the textbooks were presenting this. And so they went through, let me see, I'll bring up the table of the books that they use in their study. Those are, let's see, where was it? Sorry I know I'm gonna get you dizzy if I do this too much. I'm gonna try to, my mouse is hung up. Okay. So these are, where was the table? Okay, these are the textbooks that they use. So you probably recognize most of the textbooks that many of us are using. And so one of the things they found is that some of the books are a bit inconsistent in connecting the sources of the field, the electric and the magnetic field, to especially the variations of the field. And they found, generally speaking, that matters and interaction seem to be the one doing the best job in making the connections. And so their claim at the end is that this kind of affects the way students are understanding the field because of the inconsistencies in the way the textbooks are making this connection. But they just left it at that at this point. So, and they also are advocating for an introduction of relativity and some simplified version of relativity to try to make the logical connection between electric and magnetic fields. I'm not sure if that's doable or desirable. I don't know at this point. But that's basically what they were looking at. So I'm going to make this section a little short because I don't want to scroll back and forth all the time. But I just wanted to quickly give you a sense of what was in the textbook. So it's some of it could be maybe philosophical in the sense that they were trying to find exactly that logical connection within the topics. I'm not so sure that in retrospect, after reading this paper, that it has great impact on those early stages of trying to understand the basic setup of the electric field, and even later the magnetic field. So I'm not sure at this point that it's going to be a big issue. But here are the 2 textbooks that they think did a good job at paying attention to all those details. So that would be Matter Interactions and the 6 Ideas that Shaped Physics by I think it's Thomas More. I'm assuming you're all familiar with that textbook, maybe. Anyway, so that's as much as I was going to say on this particular section. Do you have any thoughts about the way your textbooks are affecting the way you'd like to do things in class? Do they help or not help? Even, yeah, John?
So I may have a odd take on textbooks, but for me, textbooks are for the student. I don't hold myself bound by what's in a textbook. If something's not in a textbook and I think it needs to be brought into the classroom, I bring it into the classroom.
Okay, all right, that's good. Negusi? Yeah.
I think what this article discusses is good, but I think our problem has not risen to that level. I guess I have a hard time associating the student is not being able to set up integrals related to the field. It's that much, not that much. Maybe for our, discussion, it would be helpful to pick a book, but I mean, as instructors, we clarify what we teach as much as we can, in our own way of explaining it. But our problem that we are discussing here, the student is not being able to conceptually even understand or carry out the integration of continuous charge distribution. Cannot be, I don't know. I have a hard time associating with it all to that. And it may have some part, but
Yeah, that was my feeling as well after going through this. I thought this was really dealing with a higher order kind of level of complexity that may not be too relevant, at least at the introductory level, even though they did look at introductory textbooks and they focused on but I'm not sure that this is really a significant issue for introductory physics. Yes, Theo?
I think it's probably, at this point in history, I don't expect my students to read it. I'd like them to read the textbook, but I think I asked you to raise your hands. How many of you think most of your students read your textbooks? I think most of us would say no.
Yeah, without it, you don't need the hands raised for that one.
But I think what's more dangerous is if you're a first-year teacher, like all of us were at some point, and you rely on the textbook to a certain degree when you're putting together your pedagogy, because you're assuming the people that wrote these textbooks, they must have gotten it all right at some point, or else they wouldn't be writing these textbooks. And so it's dangerous that especially, and I know I made this mistake early on in my teaching that they're mentioning it in here. And there's some things when I first looked at the textbook, like, oh, I don't think I like that, or I'm going to teach differently. And I look things up like, oh, I don't know why they're describing it this way. Like Knight does a point charge moving through space, but that's not magnetostatics. And I just don't like that. So I'm not really going to cover it that way. But this part at the end is the end of the semester when we cover E&M waves. And it's very easy for us, especially when early on in our teaching, to be like, oh, making this little mistake and not explicitly talking about the sources of these fields are the charges and currents. We might get taken in, by this little ambiguity in the textbook. So I think it's more dangerous for new instructors than it is for students, making sure that we clarify this with our students.
Yeah. So maybe one of the things that we ought to maybe share with, especially with younger faculty, is maybe don't trust too much the textbook or don't rely so much on the textbook. But I don't know if it's something that we can share right at the beginning, or is it something we need to go through anyway? And through experience, we progressively kind of distance ourselves from the textbooks after we've been completely controlled by them. I don't know how I'm assuming that's a natural evolution for most of us, is to be bound by the textbook at the very beginning and then progressively drift away from them. So I don't know. All right, so I'm looking at the clock and also what I had planned. So let me go back to my presentations here. So let me stop sharing this. And so the second part of this was to talk about visualization and simulation. So Anthony already jumped through one of them, so I'll skip that very quickly. So let me first mention why am I not able to? Oh, here we go. Okay, so I looked at a few that may be at this point familiar to most of you. So the FET, I think, are so popular that I don't think we need to really dwell on that. I'm assuming here most of you are familiar with them. The second one here was just a sort of application, what they call the electric hockey game. Let me see if I can stay within the presentation. Do you see this on the share screen? I'm always kind of worried about when I click on the link. Do you see
I can see it.
Okay. So if you're not familiar with this, this is basically a little game where the goal is to try to score actually goals.
Oh, the game isn't visible to us, just the list of links.
Oh, I see. Okay, so maybe I need to switch. Okay, so let me go back to here. Let me stop sharing this and let me do a different share. So, okay, here it is. So the idea is you have this test charge right here, and you're supposed to put it into the goal here. And because this test charge is positive, a quick and easy solution here would be to put a charge right there. And when you start, well, this one easily going to score. Okay, good. And then you go to the next level, and you go, I think, to the next level of difficulty. Now you have an obstacle here. And so how do you do that? What do you have to do then? So of course you can probably guess here that if you put some charges and you push that charge in a different way, and eventually, so I'm not going to play the game here for you, but you can get the idea. I don't think this will work, but we'll see. Yay, I did. Okay, great. I didn't really plan on it very well, but that's kind of woo. So we're 2 up, so we're good. Anyway, so that's the second simulation, and then it's actually from Ruth Shabai, and she also has it within VPython with now called Web VPython. And let me go to that one. I think I have it. Let me go to my links here. So the Web VPython, that's from the Matter Interactions. They have a whole collection. So if you are familiar with the book, you will recognize this. So it's the same general idea, pushing charges around. And I think PhET has adapted it from the Matters and Interaction textbook. Okay, so that's the other one I mentioned. Then also, the physics classroom has a whole series of activities on electric field with some simulations. And there you can see, for instance, this one, the same general idea of simulating electric charges. Okay, I want to do that here. I guess I would have to sign in. Okay, I'm not going to try here. Yeah, I'm just going to mention them here. Do you see this list of simulations here on the screen? Are you able to see that? Yeah. Okay, so they have different things. You can also recognize the hockey game is again here, very popular, and then representation of the field. And oh, this is from the PhET. So they do have a few things that could be useful, and some animations as well. So it's a nice page that kind of together brings a lot of resources for the subject. And then the one that came out very recently is from Ithaca College in New York. And a couple of interesting things about this particular simulation. I don't know if, let me see if you can see it. Let me share a screen now. So this one is a little different from the PhET simulation in that it shows electric field lines, which I found sometimes a very useful concept, especially in discussing Gauss's law, for instance. So here you have the ability to move charges. One restriction is that there are not enough lines on this side. So then you have this line that goes out and never closes back here. You can also have different configurations. So let me see if I can move my thing here. So right here on the right side of the screen, you can have either a single charge, you can have a dipole, you can have random charge distributions, and so on. You can also add the field vectors, although they're kind of tiny. It's a little hard to see them, really close to the charges. You can also modify the charges. If you click on one of the charges, you can modify the sign and the value. So it's pretty reactive. And one interesting thing about this simulation is that it was done by an undergraduate student. So this was done by someone at Ithaca College who was taking, I think, he's a physics major. And it's done by combining some JavaScript and let me see what else they used. Yeah, mostly the PJ5, it's a JavaScript library that's pretty popular with artistic design and things like that. But I thought it was well done. It's pretty recent, so there was an article about it. Let me share that with you in the physics teacher. And so here's the link to it. So the physics teacher article, that was from March of last year. Okay, back here. And let me move this screen back here. Okay, so they explained how they put together the simulation and how they're using it in class to visualize the effects. So it's I don't know if anyone has ever used the electric field simulation that used to be sold, I don't know, like 15 years, 20 years ago. It was a pretty well done simulation, but then I think it's still around, but now we use everything online, so I wouldn't buy it on a disc or anything like this. But anyway, so that's what I wanted to show you. That so, do you use any of these? Anybody uses these or other things? So Anthony showed us a new one here today that was really interesting. But what about these other resources? Yeah, Negusi?
Oh, sorry. Yeah, I use these resources, not Data College one. That one is a new one, but they are very useful. I also use one that I would like to share for
Okay.
simulation. I found it to be very good, is OpHysics.
Okay.
I'll put the link on. So this is by a retired physics teacher, and they're really nice E&M simulations. So some of them would be, for example, for EM wave propagation.
Well, I just made you a co-host. If you want to go ahead and share.
Oh, I put it there. Okay, let me see.
Yeah, just go ahead.
I think they are. Okay, let me see. So can you guys see what I'm doing?
Not yet.
So I put it on the chat. So could you just click it, Karim,
yeah,
and go to E&M area?
Yeah, let me see.
For example, go to the electromagnetic wave one.
Mm-hmm.
And you could see that's, for example, and if you click on the lower left play button,
Mm-hmm.
and it has also for charged particle and kind of motion in the B field. They have some I found it to be useful alternative ones in some areas, for example.
Okay, so let me see. I think I just had it. Oh, here it is. This is OpHysics. Yeah.
Yeah.
Okay. So yeah, this one looks like you can move the charges and
right. You can move the charges, and he has also the electromagnetic wave propagation. Charge in the B field is also well done. Motion of charged particle in the B field. So it's just an alternative, an option, a resource that you can use as well.
All right, looks good. Actually, I was thinking, Chris, we should be able to put a page with a list of resources like these for future reference so people can find them later.
Yes, so we could add them either to your to this event's main page, and we also have a resources section on our website, and I've been trying to add things there.
Well,
That would be a great place to see that.
Yeah.
So apologies, I need to run off to another meeting, so you guys have fun.
All right, thanks. Sorry. Okay, yeah, we need to kind of quickly wrap things up. So let me finish up by going then to the next item on this. So this is the so assessment of all of this. So if you are not familiar with it, the FISPort has a whole wait a minute. Why did I not get my link to work? Okay, so let me find it. I had it somewhere else. So here, yeah, this works. So let me share this part. Stop sharing this, and let's share this part. Okay, so this is from the FISPort, and they have a whole series of standardized assessments for different aspects of physics, second semester physics. So you may be familiar with the CSAM and the BEMA for electricity and magnetism. There are other things that are specialized with circuits or in different kinds of circuits. And then you have the upper level electricity and magnetism. So I think this is a pretty comprehensive list that includes most of the well-researched and established assessment tools that you can use to get a sense of, if you haven't done it already, the understanding of those topics within your classes. And so I just wanted to share this so everyone would have access to them in case you haven't seen it before. But I think we had a session on Faceport a while back, but it's always good to visit what they have on their site because they have a lot of resources. Okay. All right. So let me come back to here and simply add, maybe if you had comments or questions, because I can see the clock is like 3:59. And so I'd like to be able to end on time. So any additional thoughts or suggestions that you may have? Oh, also, Cher, do we have the feedback? Do we have the link to it? I'm sorry, I didn't really think about that earlier. Because one of the things
Chris was supposed to bring that. Let me grab it real quick.
Okay, so one of the things we also like to do on these when we have these meetings is to have a little survey so we can get sorry, so we can get participant feedback on the session on what went well, what could maybe have been done a little better, and if you have any suggestion for other things we could do within this format. And so I think we should be able to have this in the chat. It only takes a couple of minutes.
2 seconds while I pull it up.
Yeah, I know. So anyway, I'm going to stop sharing at this stage. And any other thoughts about what we discussed today? You will come back next month. We have our session on scientific reasoning and labs. And yes, Richard?
Can you hear me?
Yes, we can. Yeah.
Okay, good. I just, like to think about, how Michael Faraday thought about fields. He famously wasn't any good at math. And so he thought of things, I think very visually. And, while we do want to enable our students to solve complicated problems, I figure it's a good idea, for them to develop an intuitive sense of simple, situations. Why does it make sense that the electric field between two very large parallel plates is uniform? Mm-hmm. Why is it that the electric field near an infinite line of charge drops off with the first power of the distance? And think about the geometry of the situation, that you could think of a line of charge. Well, where for every positive charge that's on that line, somewhere in the universe, there has to be a negative charge. Well, why not make it reside on a cylinder that surrounds the line of charge? And I think from there, my experience with, non-calculus students is that some of them at least get the idea, oh, I see, the lines of force will be radiating outward, and the crowdedness of the lines, the density of the lines, or the points where they intersect a cylinder, will decrease with the first power of the radius. And then finally, a point charge, where's the rest of the charge? It's on a sphere. That's where you moved it in order to have that point charge have a charge. You have to do something with the electrons. So you put them on this sphere, and naturally they spread out over the sphere, and you draw lines. And so the force decreases as the area of that sphere increases. There's an outer sphere, and we're talking about the force, on an inner sphere. I don't know. I'm just curious to know if other people use those kinds of reasoning strategies before getting into, the integrations.
Yeah, that's a good point, that we seem to be focusing so much on the calculation side of things that the visual part of it should be also emphasized as much. And especially since we focus here on the calculus-based courses, but there's a whole other part of physics courses which are more algebra-based and not really ready for this kind of math manipulation. And yet we also do some field discussion in those courses. So I'm wondering, do you adopt different strategies for introducing those notions in either calc-based or algebra-based? Do you do it?
Yeah,
what's the-
I mean, yeah. You're asking me or everybody?
Yeah, anybody who would, yeah, go ahead, Richard. I'll be curious to hear what you.
No, I teach mostly algebra based at
Okay.
this point. I just have a little calculus based but I want them to understand, to think spatially and visually also, and then to see how the result from calculus makes sense.
Yeah, okay. But how about those who teach both of those courses within the same semester? Does that generate this sort of dissonance or a need to do some back and forth switching? Because sometimes it feels, once you're comfortable with a certain type of presentation, you want to use the same thing, but you have to realize the audience is different. They may not react to the same arguments the same way. Symmetry, we talked about symmetry earlier, and it's sometimes a little hard concept to take advantage of, and I don't know, we don't seem to.
I think
we
not
should-
having that visual skill is part of the reason students have trouble doing the integration.
Yeah,
And so it's important to build up some of those ideas as well, or else the integration is meaningless.
yeah, it's true. Yeah.
Yeah, I think, yeah, I do that as well as much as possible, in both, why is it falling like this? What happens to the fields? I mean, every time I think the conceptual building of these things is very important, otherwise, it even creates more problem when they try to do the integration. So as much as possible, I also do the conceptual part, emphasize that is important. Unless they understand the conceptual one, it just becomes a meaningless mathematics exercise. So yeah, as much as possible. Yeah.
Okay.
I'm going to share the link to the download.
great.
I'm going to share my screen. I have it up.
Yep. Go ahead.
Okay, there you are.
All right. Perfect.
So please provide your feedback. We appreciate that you were here today.
Yep. So yeah, it only takes like 2 minutes or so, right? It's a pretty short exercise. Oh, you're muted. Sorry, Sherry.
Yeah, it's a very short little, a couple, 2 or 3 questions, and we appreciate it. And I'm going to go ahead and stop recording.
Okay.